In this video, we will introduce differential forms, show that they form vector spaces, and define operations like the wedge product and the exterior derivative, and study the structure that those operations introduce. Then we will define the Levi-Civita tensor and discuss the duality between differential forms related to it. P-forms are important because we can do some calculus without introducing additional structure to a differential manifold. We will show that they can be differentiated, and in a following video we will show that they can also be integrated. The properties also are related to the topological properties of the manifold as a topological space. Let's start by considering 0p type tensors, and let omega be one of them. If sigma is a permutation of the integers 1 through p, then we can define a new tensor sigma omega by its action on p vectors v1 through vp to be equal to the action of omega on the permuted set of the vectors. Then we can compute the components of the new tensor sigma omega by considering the action of omega and sigma omega on a basis, on a chosen basis. So the components of omega are given by the action of omega on mu1 through mu p, and similarly the same is true for sigma omega. But by considering the definition of sigma omega, we see that the components of sigma omega are the same as those of omega with the indices permuted by sigma. From any 0p type tensor, we can define an antisymmetric tensor, which we will call now A omega. Consider all possible permutations of integers 1 through p, and form all the possible tensors sigma omega for all sigma, and multiply that by the sign of the permutation. Then this will be a completely antisymmetric tensor, and its components can be found to be equal to the components of omega that have been antisymmetrized with respect to all of their indices. We define a p-form to be a completely antisymmetric 0p type tensor. Therefore, its components will be completely antisymmetric under the exchange of any of its indices. We can define a product on the space of forms, of differentiable forms. And that is important because not any product would multiply two forms and give us back forms. For example, the tensor product does not. So the wedge product can be defined by considering first 1 forms. And let's consider p of those, so that we form a p form by multiplying p forms under this product. So this product is defined by the right hand side of this equation, where we take all possible permutations of those vectors, then we tensor multiply them, and we weigh that with the sign of the permutation. So that will give us p factorial terms, and of course this product will be antisymmetric with respect to the exchange of any of the factors of the product. Notice also here that we introduce no normalization in front of the sum. From the definition, we can immediately see that if two factors of the product here are proportional to each other, then the wedge product is 0. Because, as we have already said, the product is antisymmetric with respect to the exchange of any of its factors. So if we exchange mu1 and mu2, we obtain a minus sign. But if mu1 and mu2 are equal, then that should be equal to itself. So something is equal to minus something only when something is 0. So this wedge product will necessarily be equal to 0. And from that we conclude that if the E mu I are linearly dependent, the wedge product is also equal to 0. And that can be easily seen by expressing any of those as a linear combination of the others, which is possible because they are linearly dependent. And we substitute that in the definition of the wedge product. And by the linearity that the wedge product has, we see that every term contains at least 2 equal vectors. And so each term is equal to 0 separately, and the wedge product is 0. We also see that for the wedge product to be non-trivial, that is to be possible to be non-zero, p must be less or equal to n. If we choose p greater than n, then necessarily this set of vectors will be linearly dependent. Therefore, the wedge product will be equal to 0. If we form linear combinations of such wedge products with the components of a symmetric tensor, we will obtain 0. This is symmetric under the exchange of mu and nu, and this is antisymmetric. Therefore, this sum here will have terms that will cancel each other and give us 0. And that is true if we take any 0p type tensor and form this linear combination with the wedge product of the vectors E mu I. And if this tensor is symmetric under the exchange of any of its indices, then this will be equal to 0. So we conclude that if we take any 0p tensor and form linear combination with this wedge product here, then this wedge product will select only the antisymmetric part of the tensor here, because the symmetric part will contribute only 0. So let's see now why p-forms form a vector space. Let's consider any tensor, and we know that if we choose a basis, coordinates, then this defines a basis in the cotangent space, the dx mu basis, and then omega can be written as a linear combination of the tensor product of dx mu, and these are the components of omega in this basis. If omega happens to be antisymmetric, then all those terms will be equal to each other, because here omega is simply antisymmetric. So summing over all permutations, we obtain the wedge product, and the left hand side will give us p factorial times omega. Therefore omega is 1 over p factorial times the wedge product multiplied by the components of omega. So any p-form can be written as a linear combination of those vectors here. But those 0 p tensors, dx mu1 wedge up to dx mu p, are not linearly independent to each other. And this is because under the exchange of any of those, we simply change the sign of the vector. So in order to form a basis, first we have to choose all these indices to be different, and consider the fact that under the exchange of the order of any of those vectors here, we will obtain the same vector up to a sign. Sorry, vector, I mean in the vector space lambda p, a 0p tensor. So we will soon see that this means that we have to consider the combinations of the p indices, which are take n values, and we know that the number of those combinations is given by the binomial coefficients np. Indeed, first we have to choose all those indices to be different, and this can be done in n factorial over n minus p factorial ways. So these are the possible permutations of p objects that take n values. So the first one can take, the first index can take n values, and after we have picked up the first index, the second index takes n minus 1 values. That can be done in n times n minus 1 ways, and by filling in the slots here, we end up with no choice with the last index. We just have one choice, the index that is, we have n minus p plus 1 choices here. So the total number of ways is n times n minus 1, n minus p plus 1, and by multiplying and dividing by n minus p factorial, we obtain that the number of ways that this can be done is n factorial divided by n minus p factorial. But as we have already said, permuting those indices here give us back the same element of the vector space up to a sign. So we have to consider combinations and not permutations of indices. And to obtain this, we have to divide by the p factorial permutations of the chosen indices in the p slots, and we obtain the binomial coefficient. So we have shown that any p form can be written as a combination of np linearly independent vectors given by the wedge products of dx mu. So that forms an np dimensional basis. So the space of p forms is an np dimensional vector space. Let's see some examples here. For p equals 0, we have 0 forms, and the dimensionality of lambda 0 is equal to 1. For p equal 1, we have 1 forms, and we have already seen that this is an n-dimensional vector space. And for p equal n, we have only a one-dimensional vector space. So notice that there are no non-trivial p larger than n forms, because if we form an object that has, let's say, n plus 1 indices that take n values, then at least 2 of those have the same value. So this cannot happen if this object is completely antisymmetric, except if it is 0. We also notice that lambda p and lambda n minus p have the same dimensionality, and the two spaces are vector spaces that are isomorphic. And an important observation is that the space of n forms is one-dimensional. So that means if we take any non-trivial n form, then all other n forms will be proportional to it. And for example, if we choose dx1 wedge up to dxn, then all forms will be proportional to this n form. Let's consider 3 dimensions as an example. Then lambda 0 is 1-dimensional, lambda 1 is 3-dimensional, lambda 2 is also 3-dimensional, and lambda 3 is 1-dimensional. So we see that in 3 dimensions, the 2 forms and the 1 forms are belonging to spaces that are isomorphic. And that is why we can define a cross product in 3 dimensions, and we cannot do so in higher dimensions. So let's see this, why this is true. If we consider 2 1 forms, omega and sigma, then their wedge product is given by definition by this formula. So if we expand the summation over mu and nu here, we will end up with a linear combination of dx1 wedge dx2, dx2 wedge dx3, and dx3 wedge dx1. And because dx1 times dx2 is minus dx2 times dx1, this common factor here has the components multiplied together but with a different sign. Now, if you remember the cross product from high school, then you would know that the components of the cross product are given by this expression here. So the 1 component here has 2 and 3 components, 2, 3, 1, and 3, 1, 2, and you see all the plus signs have 1, 2, 3 in a forward cyclic way, whereas the minus signs have the order in the opposite way, like 3, 2, 1, 3, 2, 1, 3, 2, 1. Now, if you compare those 2 expressions, you see that the dx1 wedge dx2 component is the same as the dx3 component of the cross product. And similarly, the components of omega wedge sigma are the same as those of omega cross sigma. So there is a 1-to-1 correspondence between cross product and wedge product. Let's also write the expressions for the 1, 2, and 3 forms here. For p equal 1, we have 3 numbers here, omega x, omega y, omega z. For p equal 2, we also have these 3 numbers, omega xy, omega yz, omega zx. And if we want, we can define omega yx, for example, being given by minus omega xy, but we have only 3 independent numbers. And for p equal 3, we only have 1 number because we have a 1-dimensional vector space. Since we have defined p forms on any point of the manifold M, now if we make this construction to be smooth over the whole manifold, then we can have p-form fields. Notice that n-form fields are special, since at every point 2 n-forms are proportional to each other. That means that n-form fields will differ at all points only by a function on M. We can see this explicitly by considering a nowhere vanishing n-form field, let's call it epsilon. Then any n-form field omega can be written as f times epsilon for some function f on the space of functions on the manifold M. So let's generalize now the definition of the wedge product for any 2 differential forms. let omega be a p form and xi be a q form, then we define omega wedge xi to be a p plus q differential form. And we define this form by its action on p plus q vectors, v1 through v plus q. And for that we consider all possible permutations of those vectors, v1 through v plus q, into the slots of omega and xi. Omega has p slots, xi has q slots, but the v's are permuted over the slots of both differential forms. And we have p plus q factorial terms, each weighted by the sign of the respective permutation. We also choose this normalization here that comes from the p factorial because omega is a p form, and q factorial because xi is a q form. These are introduced just for convenience, of course. So let's see what the components of the wedge product is. So omega wedge xi has p plus q indices here, and they can be computed by considering the image of p plus q members of the coordinate basis dx mu. We apply the definition of the wedge product here and put the dx mu's in the slots of omega and xi in all possible different ways. But its factor here corresponds to the components of omega and xi with the indices permuted by sigma. And if you remember the definition of the antisymmetrization of indices, this is equal to p plus q factorial times the antisymmetrization of the indices of omega times xi. So this p plus q factorial comes because here we consider all possible permutations but normalized by p plus q factorial. And there is no such factor here, so we add it there. Therefore, from that we can read off the components of the wedge product, omega times xi, and there is this funny normalization here, p plus q factorial, p factorial, q factorial. That makes this expression slightly complicated, but it simplifies other expressions, so well, there's no free lunch. Other books choose different conventions, but we will stick with those. So, since these are the components of omega wedge xi, then we can write omega wedge xi in terms of its components in this form, as we can do with any p plus q form. So if we substitute the expression we just computed here, the p plus q factorial cancels out, and omega wedge xi can be written as the linear combination of the products of the components of omega and xi. Of course, here we have those brackets, but because the wedge product selects only the antisymmetric part of an expression, we can remove the brackets from this equation here. So whether you put them or not, the result is the same. So we have two expressions here. The components of omega wedge xi is given by this equation, and omega wedge xi expressed in terms of a coordinate basis is given by this equation here. So we have this p factorial and q factorial coming from the p form omega and q form xi. let's see some examples. Let's consider omega and xi. Omega is a 1 form, xi is a 2 form, and the wedge product will be a 3 form. Then we will show that the components of omega wedge xi is given by the sum of the products of the components, where we take all possible permutations of the indices, but with positive sign. So you see here, if I consider mu, nu, and rho on a circle and go in the clockwise direction, then we have all possible combinations: mu, nu, rho, nu, rho, and nu, rho. So we have those three terms surviving in the end. Okay, so let's see why this is true. From the formula for the components of the wedge product, we have this equation here. Now this is 3 factorial divided by 2 factorial. It gives a 3 factorial here. And this is the product of the components of omega and xi with the indices antisymmetrized. So the antisymmetrization of indices entails a 3 factorial here in the denominator. Now we write all possible permutations of the indices, but with the sign of the permutation. Notice here that we can simplify this expression, and all the permutations with negative sign will be the same as the ones with the positive sign. So we will have twice the sum of the first line here with the pluses. So we have a factor of 2 that will cancel the 2 coming from the 3 factorial. The 3 cancels with the 3 of the 3 factorial, and we end up with this simple expression. So we see that with our conventions, the wedge product ends up having components without any factors in front of it. Let's see some of the general properties of the wedge product. First of all, the product is associative, so it doesn't matter which order we choose to compute it. We can compute first the wedge product of xi and eta and then with omega, or compute first omega with xi and then with eta. The wedge product has also the funny property of being graded anti-commutative, as it is said in mathematics. Omega and xi is the same as xi multiplied by omega up to a sign, and the sign depends on the type of omega and xi. So if omega is a p form and xi is a q form, the sign here is given by minus 1 to the power p times q. And that leads us to the conclusion that omega wedge omega with itself is 0 whenever p is odd. And the reason is that omega wedge omega, if we apply this anti-commutative property here with itself, then it should be equal to omega wedge omega, but with a sign minus 1 to the p square. But if p is even, that is a plus sign, so this is a trivial identity. But when p is odd, then this is minus to itself. So this is possible only when omega wedge omega is equal to 0. So we see that the wedge product has the property that takes us from two forms, one could be a p form, another being a q form, and gives us a form of higher degree. So this gives the direct sum of all the spaces from 0 forms to n forms a graded structure, because if we take the wedge product of a p form and a q form, this is a p plus q form. So this direct sum here has a special name. It's called the Grassmann algebra. And just so that I make sure that you understand what I have written, let me remind you what is the direct sum of two vector spaces. So the direct sum of two vector spaces V and W consists of pairs of vectors, one belonging to V and one belonging to W, with the operations of addition and multiplication being defined in an obvious way. So this lambda star algebra here consists of tuples of forms, the first one being a 0 form, 1 form, up to an n form. So this is closed under the operation of the wedge product, and it forms a nice structure. So now let's prove the anti-commutative property of the wedge product. So we start with two forms, omega being a p form and xi being a q form, and we choose a coordinate basis dx mu to write down the expressions in terms of their components. So omega times xi is obtained by multiplying omega and then with xi. So we see here that we have an expression that involves the product of the components. That of course is commutative, but then the wedge product of the basis elements here comes in the order mu1, mu p plus 1, mu p plus q. Now if we form the product xi times omega, then this will come in the opposite order. So we will have again the product of the components. This doesn't matter, it's commutative. But then we have the wedge products of the basis elements in a different order. So we start with dx mu p plus 1 coming from xi. We go up to xi mu p plus q, that comes from the xi q form. And then we have the wedge product of dx mu 1 through x mu p. So in order to compare those two expressions, we have to move all those factors here to the front to obtain the same p plus q form as in the first expression. So we do that in steps. First, we take dx mu 1 and we bring it up to the front so that it agrees with this wedge product. But in order to do that, we have to jump over Q1 forms. So each time we do that, we change the sign. So after we have finished, we have changed the sign of the expression by minus 1 to the Q. Okay, we have Q1 form, so the sign changes by minus 1 to the Q. Then we have to take dx mu 2 that follows dx mu 1, and again move it along the Q, the product of Q1 forms, each time again changing the sign by minus 1 to the Q. So after we have done that, the total change of the sign will be minus 1 to the 2 times Q, 1 for each motion. And then we go on with the following 1 forms. Dx mu 3 is moved here. The sign is changed again by minus 1 to the Q. Therefore the total sign change is minus 1 to the 3Q. And after we have moved all P 1 forms from the back to the front, the total change of sign will be minus 1 to the P times Q. Therefore, we have proved that the change of sign here is exactly this factor. Let's now consider exterior derivatives. For that, let's start from p-form fields in the space lambda p and define the exterior derivative as a map from lambda p to lambda p plus 1. So it will take a p form and give us back a p plus 1 form. And the definition will be the following. If I choose a basis, let's say a coordinate basis, dx mu, I can write omega in terms of its components this way. And the new form, which is a p plus 1 form, d omega, is obtained by differentiating the components with respect to the x nu coordinate and adding here a dx nu on the wedge product. So we have made some choices here. First is not to put here any normalization factor and to put dx nu on the front rather to some other position in the wedge product. So these are conventions because they all lead to equivalent definitions. Now let's notice that if we multiply and divide by p plus 1, we obtain here p plus 1 factorial and p plus 1 on the numerator. And observe that this is nothing but the components of a p plus 1 form when written in terms of the wedge product of the coordinate basis. So from that we conclude that the components of the exterior derivative of omega are given by p plus 1 times the derivative of omega with respect to dx nu with all the indices here antisymmetrized. Of course, mu1 through mu p are already antisymmetrized, but nu here has to be antisymmetrized. Now, if we write this expression here, then we don't have to put the antisymmetrization brackets because this is taken care by the wedge product dx nu through dx mu p. Let's compute some examples. The exterior derivative of a function is simply the derivative of the function. The exterior derivative of a 1 form is given by this expression here. It has two indices. It's a 2 form. So that is 1 plus 1, 2. Then you see we have to antisymmetrize the mu and nu indices. So we have 1 over 2 factorial to normalize with. And here the antisymmetric sum of the permutation of the indices. So we end up here with d mu omega nu minus d nu omega mu. So with the conventions chosen, there is no factor in front of here. Similarly, we can compute the components of the exterior derivative of a 2 form. So this will have 3 indices. It is a 3 form. So that is 2 plus 1 here times the antisymmetrization of the indices of the derivative of the components with respect to dx mu. So we write here all the possible permutations. Notice here that those terms are equal. If you change nu rho with rho nu, this minus becomes a plus. So we obtain twice this term here. So the end result will be that the components of d sigma are simply the derivatives of the components of sigma with all the positive permutations of the indices. some fundamental properties of the exterior derivative, the way that we have defined it, is first of all linearity. Alpha and beta here are real numbers. And also we see that it has a kind of Leibniz rule that derivations have, but not quite. The reason is that if D acts on the wedge product of two forms, then we obtain the sum of the action on each one of them, but there is this funny sign here, -1 to the p, where p refers to the order of the first form. So this is not a derivation, but it is called an anti-derivation because it is very important too. The operator D is nilpotent, which means that when it acts twice on any differential form, it gives 0. So we have defined the exterior derivative by showing how it acts on components, but don't worry, any anti-derivation that has the above properties and with the definition of its action on functions determine this operation uniquely. So it doesn't matter how we exactly make this definition. So let's show some examples of those properties. Let's consider two one-forms, omega and xi, and their wedge product, omega times xi, which in a coordinate basis is given by this expression. Then the exterior derivative of the wedge product is obtained by taking the derivative of the components here and putting an extra dx factor in the wedge products. So that, of course, is because it is a 3 form. But the derivative here acts on the product in the usual way. We apply the Leibniz rule for ordinary derivatives here. And now you see the first term here has the components of d omega and xi, and we have dx rho, dx mu, dx nu. But in this case, that we want to have the exterior derivative of xi, we have the rho index in let's say the wrong position. So in order to put it in the correct position, we have to swap those two one forms, and instead of dx rho dx mu, we write dx mu times dx rho, but the penalty is a minus sign. So if we do that and group the terms as shown here, so that is d rho omega mu times dx rho dx nu, and then xi nu goes with dx nu, and similarly here omega mu is paired with dx mu and the derivative of xi with dx rho dx nu. So each factor in the parentheses gives us the corresponding differential form. So this is d omega here, and this is xi, whereas this is omega and this is dxi. So we have shown the anti-derivation property of the exterior derivative, and also we have understood why this minus sign comes. It was because we had to move dx rho from this position to move it over one position, because this is a one form, and obtain a minus sign. In the general case, omega will be a p form, so the index here that corresponds to the derivative has to jump over p indices. So instead of a minus sign here, we will obtain minus 1 to the p. Now let's consider d omega, that is a 2 form. Now, if we dare to differentiate this once more, then by applying the definition of d, we will simply have to compute the ordinary derivative of d mu omega nu and put here a dx rho. But this is nothing but the second derivative of omega, which we always assume that it is symmetric under the change of the order of the derivative taking. And because dx rho and dx mu are antisymmetric with respect to the change of their position because of the antisymmetry of the wedge product, this will necessarily give us 0. So this is easily generalized to any p-forms. If you take the exterior derivative of any p-form and then differentiate it once more, then you will have a second derivative here, and then you will have the product of dx's with the indices matching the derivatives. So this will always be symmetric, and this will always be antisymmetric. So now let's consider another operation that instead of moving us from p-forms to p+1 forms, will move us from p-forms to p-1 forms. For that, we'll have to consider the contraction of a p-form with a vector. So this operation will be defined with respect to a chosen vector in the tangent space at a point, or if these are fields, that's a vector field, and that is a p-form field. Doesn't matter for this definition. So if we choose a coordinate basis, then v is written in terms of its components, and coordinate basis d mu, and omega in terms of the wedge product of the one form basis dx mu. So the contraction of omega with v, or the interior product of omega and v, is simply the contraction of omega with v put in its first slot. So as you see, this operation leaves p-1 slots empty. So it just occupies one slot. So that will give us a p-1 form, because after the contraction, the remaining slots are antisymmetric with respect to the positions of any vectors that you will put there. Furthermore, we have chosen the first slot for the contraction, but if we had defined the contraction with respect to any other slot, this would be essentially the same thing, and only a change of sign would occur. We know very well that if we contract any 0p tensor with a vector, the components are given by the contraction of the respective indices. So the index of the vector here is contracted with the first index of the component of the p form here. So since these are the components, then we know that since this is a p-1 form, it can be written in terms of the wedge product of the dx mu basis, like that. And some properties of this interior product is that it takes us from lambda p to lambda p-1, and we can go on to smaller p's if we want. Now, if we act with this operator twice, then we obtain 0 because of the antisymmetry of the p form. So if there were here a second factor v mu contracted with mu2, then the product would be symmetric, but the exchange of indices here antisymmetric, and the result would have been 0. So this is again a nilpotent operator. The contraction is also related to the Lie derivative of the P form, and the useful identity for computations is that the Lie derivative of one form is the same as the anti-commutator of the exterior derivative with the IV operator. Furthermore, the action of the Lie derivative and that of the contraction commutes. So let's describe, and scratch the surface of course only, of why P-forms are related to the topology of the manifold. So we observe that the operation of the exterior derivative induces a sequence between vector spaces. We have here the 0 vector space, which by the inclusion map can be mapped to lambda 0. Then the exterior derivative lifts us to lambda 1, and then again to lambda 2. We go to lambda n, and then if we apply d once more, we obtain always 0. We go back to the 0 vector space. As we have already mentioned, D is nilpotent. So if we have a P-form that is the D of a P-1 form, then it is trivial that its exterior derivative will be 0, because that would be the second derivative of omega. But the reverse is not true, which means that if df is 0, then it does not necessarily mean that there is a P-1 form whose exterior derivative gives f. So we give the following definitions. If we have a P form whose derivative is 0, we say that this form is closed, and we call the space of such forms ZP. And if a P form can be written as the derivative of a P-1 form, then we say that f is exact, and we call the space of exact forms, of exact P forms, BP. Then an equivalence relation can be defined for closed forms. So if F1 and F2 are closed forms, we say that they are equivalent if their difference is an exact form. So we can form the quotient space of ZP by BP by this equivalence relation, and this is called the pth, the RAM cohomology of the group M. So this cohomology group is related to the homology group of the same order of the manifold M, which we know are groups that reflect the topological properties of M as a topological space. So if we have two spaces that have different homology groups, then we know that they are not topologically equivalent. Now let's consider the Levi-Civita symbols. So we define the symbols epsilon tilde of n indices, mu1 through mun, to be the ones that take three possible values. They are +1 if their indices are an even permutation of 1 through n, -1 if they're an odd permutation of 1 through n, and 0 otherwise. The otherwise case consists of cases where two or more indices are the same. So this is a completely antisymmetric symbol. So we have to make clear in this lecture we were not so clear before in previous ones, that these are not tensors, they're just symbols. So that means that if we choose any basis, then they have the same value. They're just symbols to indicate plus ones and minus ones and zeros. Also, the indices here are placed upstairs or downstairs according to our convenience. It doesn't matter if all or some of them are upstairs or downstairs, the symbol is defined always the same way. In order to do algebra with Levi-Civita symbols, we have to, it is very useful to see their relations to Kroneker's deltas. So let's take, for example, the two-dimensional Levi-Civita symbol. So we have two indices here, taking two values, 1 or 2 or 0 and 1, it doesn't matter. And the product of two of those can be expressed as a linear combination of products of two Kroneker's deltas. So there is an easy way to remember how to do that. Since we have two indices, we have two deltas here for each term, and we also have two terms. Then the lambda rho indices are chosen to be in the same position in both terms, and then we permute the order of the mu and nu indices. So if we have an even permutation, we put a plus sign here, and if we have an odd permutation, we put a minus sign here. And this simple identity is very useful when we want to contract one of those two indices. So if we want to contract the second index here, nu and nu, so we form the sum of all these epsilon square terms for all values of nu, then the result can be calculated using the right hand side of this equation. So here ni and rho have the same value, so we have nu and nu here, and here we have nu and nu. Now delta nu nu sums ones for all values of nu, which are two values here, so symbolically n. So that will give us n times delta lambda mu. And this term here will simply select non-zero terms when lambda and mu are equal only. So we will have again delta lambda mu. So the end result is n minus 1 times delta lambda mu. So without proving it, but just stating it, the epsilon square identity generalizes for any value of n. So if we consider epsilon nu1 through nu-n and epsilon nu1 through nu-n, we have an identity relating it to deltas, Kroneker's deltas here, and what we do, we have here n factorial terms which are formed by considering products of n such deltas. Now the indices here upstairs are put in the order of the epsilon symbol with the indices chosen to be upstairs, and then the indices downstairs, mu1 through mu-n, are anti-symmetrized. So here we have 1 over n factorial times the products of these with all indices mu1 through mu-n permuted and multiplied by the sign of the permutation. So this n factorial put here cancels the 1 over n factorial from the operation of anti-symmetrization. So it is convenient to define the p delta symbol to be this for any p. So instead of having only definition for n indices here, which of course is needed for the Levi-Civita symbol, we define this generalization of Kroneker's delta for any p. So we write here products of deltas. It has p factors. The upstairs indices are nu1 through nu p. Sorry, this is a typo here. And here we have nu1, nu2 through nu p. So when p is equal to n, you see that this expression here is equal to the n delta symbol. So here is the definition of the p delta symbol, and let's write now formulas that are obtained by contracting to such indices. So we can contract any indices here, taking care of signs, of course. So we will show just contractions with respect to the first index, the first two indices here. So we contract nu1 and nu1. Here we have lambda 1 and lambda 1, they're the same. And we have p minus 1 free indices on the left hand side. So that will give us, after computation of course, the p minus 1 delta symbol with indices nu2 through nu p, nu2 through nu p. But we will also have a factor n minus p plus 1. So this comes from the fact that these are p minus 1 free indices, and this is n minus the number of the free indices. Then we can go on and contract more indices. So here I also contract the second indices. So this is obtained from this formula by contracting the first indices here. So if we apply the formula in the previous line, we obtain n minus p plus 2 now, and the p minus 2 delta symbol. So we have here the product n minus p plus 1 and minus p plus 2. And we can do that for any number of indices, but at some point there are no more indices left, and if we contract all indices, then in the end the last factor that we obtain by increasing this by 1 at each step is n. So you see that this is nothing but n factorial divided by n minus p factorial. It is useful to write those identities when p is equal to n. So the first line is simply the definition of the n delta symbol. Now when we contract the n delta symbol with respect to one index, then n minus p plus 1 simply gives 1, and here we have the n minus 1 delta symbol. Then if we go ahead and contract this once more, then n minus p plus 2 will give us a 2, and so on. And if we go on and contract all indices, we will obtain n factorial. So let's apply those identities to the contractions of the Levi-Civita symbol. So as we have shown, the first line, so we have not shown, but as we have written in the previous slide, the product of two epsilons is equal to the n delta symbol, or equal to this expression here. So when we contract the first indices of the product of two epsilons, then we will obtain the n minus 1 delta symbol, which is equal to this. And then if we contract the second index, then we will obtain twice the n minus 2 symbol, which is equal to this. And if we go on and contract all indices in the end, we will obtain n factorial. So this is an important identity. Notice that those funny factors here, which we absorbed in the definition of the p delta symbol, are simply simplifying these factors that come from the symmetrization. So when we expand those formulas, in the end, those factorials here will cancel. The Levi-Civita symbols are very important because they are related to the computation of the determinant of a matrix. So if we consider an n by n matrix, then we know from linear algebra a very important identity that relates the determinant of a matrix to a product of n factors of its matrix elements. So what you see here is we sum over the indices of the rows of the matrix and consider all possible permutations of those, and multiply here essentially by the sign of the permutation. And what we are left with is the determinant, but up to a sign. And the sign is determined by the permutation of the indices mu1 prime through un prime, and given here by the corresponding Levi-Civita symbol. So if we use the identity that epsilon times epsilon contracted over all n indices gives an n factorial, and we contract both sides of this equation by an epsilon symbol, then we can solve for the determinant and obtain this formula here. And this n factorial comes from the contraction of the two epsilon symbols on the left hand side. Notice that in this formula that I have written the indices of the Levi-Civita symbol that was on the left hand side before and had the indices downstairs, but when I put them here I place the indices upstairs. So as we have already said, these are not tensors, they are symbols, so it doesn't matter where the indices are placed. So let's apply to this formula when the matrix A gives us the derivatives of the coordinates in two different coordinate systems. So let's call the matrix A mu prime. Let's define the matrix A mu prime now to be the derivatives of the x mu's with respect to the x mu primes. So if we substitute the first formula here, we obtain this relation here, where we denote the determinant of this matrix of derivatives by these vertical lines. This is called the Jacobian of the transformation. And you see that we can carry the determinant over to the left hand side. Of course this is trivial because it is a number, but it will go to the denominator. But if we observe that the inverse of this determinant is simply the determinant of the inverse, where the inverse is the matrix of derivatives of x mu prime with respect to x mu, we arrive at this very useful formula. So if we have the Jacobian multiplied by the anti-symmetrized product of those derivatives here, we will obtain a Levi-Civita symbol. And of course, we can also compute the Jacobian using this formula as with the determinant of any other matrix. Using the Levi-Civita symbols, let's now define the Levi-Civita tensor. So we have to make sure when we do relativity that we understand the difference between those, which is not so important when we are in flat space. For that, we need a metric on the manifold, and we have not defined metrics yet, but let me consider here the essential properties that are necessary for the discussion. So a metric is simply a 0-2 tensor for our purposes, which is symmetric and non-degenerate. That means that its determinant is nowhere 0, and it can be inverted. We will denote the determinant of the matrix of the components of this tensor by simply the letter G, and the components of the inverse will be written with the letter G without the -1, but placing the indices upstairs instead of downstairs. So the definition here of the inverse simply states that if we multiply the mu matrix elements with the nu lambda, we will obtain the diagonal matrix, delta mu lambda. Another property of the metric that has to be considered is the signature of the metric. Since the metric is non-degenerate, its eigenvalues are non-zero, and it can be shown that the number of negative eigenvalues does not depend on the choice of coordinates. So it is something that characterizes the metric, and it's called the signature of the metric. The sign that comes from -1 to the s will also be called the signature of the metric. We have to understand the two differences here. And notice that since this sign is the same as the sign of the determinant, because the determinant is the product of the eigenvalues, then we can write that this sign is equal to G divided by the absolute value of G. So let's see how the tensor behaves under a change of coordinates. Then the coordinate basis is changed, and the coordinates are x mu and x mu prime respectively. So the components of G in the coordinate basis dx mu prime are related to those in the dx nu basis by this transformation law, and by defining lambda mu prime to be the matrix that has rows and columns formed by the derivatives of x with respect to x prime, I can write this relation like that. And if I move G into the middle here, which is trivial, everything here is a number, you see that this index here matches that index. So this product here corresponds to the product of the matrix G and lambda, but the index mu here is matched with the wrong index of lambda. So that is correspond to the row of lambda and that to the row of G. So what I will do is I will consider the transpose of that matrix. So rows and columns are exchanged. So mu moves to the row slot, and mu prime moves to the row slot, and mu to the column slot. And then you see that the indices are summed, so rows are multiplied by columns. So this expression here can be obtained by computing the product of those three matrices, and that will give us the components of G in the new coordinate system. So the determinant of the matrix formed by those components is equal to the determinant of the product of those three matrices. Therefore, since the determinant of the transpose is equal to the determinant, we arrive to this formula saying that the determinant of the metric in the new coordinate system is equal to the determinant of the coordinate in the previous coordinate system multiplied by the Jacobian square. So let's use this notation, G prime for det G prime and G for det G, and lambda is the Jacobian dx by dx prime. So we see that the determinant is not a scalar because it transforms when we change the coordinate system. And similarly, if we want to see how the square root of the determinant transforms, then we have to use here the absolute value of the Jacobian. So we are ready now to define the Levi-Civita tensor. This is obtained in a given coordinate system that we have chosen by multiplying the Levi-Civita symbol, which is always plus and minus 1 and zeros for same indices, and the value of the square root of the absolute value of the determinant of G, which is a number that depends on the coordinate system chosen. So every time I change coordinate systems, this will not change, but this will change. So let's prove that this is indeed a tensor, and for that we will compute its transformation properties. So let's take epsilon and multiply it by the derivatives of dx with respect to dx prime. We substitute the definition that we have just given here. But then we notice that those two terms here will give us the determinant of this matrix, that means the Jacobian of the transformation, times the Levi-Civita symbol with the primed indices here, mu1 through mu1 prime through mu n prime. But as we have seen, the square root of G times the Jacobian gives us the value of square root of G prime in the new coordinate system up to a sign. So for this to be a tensor, we have to consider coordinate transformations that are, as we say, orientation preserving, and their Jacobian is positive. Then we see that the left-hand side is equal to the components of this tensor in the new coordinate system. Therefore, the Levi-Civita tensor is a 0n tensor. It is, of course, completely anti-symmetric, therefore it is an n form defined on the manifold. And as such, I can write it in this form, considering the components that I have defined it to have in any coordinate system. Notice also that because I have chosen G to be such that its determinant does not vanish, this is a nowhere vanishing n form. And that is an important property, as we will see. The existence of a metric allows to have a map between forms and vectors. And this map is obtained by doing the so-called index raising and lowering. So as an example here, we will use the Levi-Civita tensor that has n indices, nu1 through nu-n, and define a completely antisymmetric tensor whose indices are now upstairs. So this is an n form. This is an n0 completely antisymmetric tensor, which we call an n vector. So in order to obtain this n vector, we have to raise its index separately by multiplying by a factor for each index that contracts one index from the inverse metric with the chosen index, and the free index here is the new index of the object on the left hand side. So you see here a downstairs index is mapped to an upstairs index. And we do that for all indices of the epsilon symbol, including the last one, where again we see that we contract the downstairs index with an index of an inverse metric, and the free index here becomes the last index of the n vector on the left hand side. So if we substitute the value of the components of the Levi-Civita tensor, square root of g times the Levi-Civita symbol, then we observe that this is nothing but the determinant of this matrix. But be careful, this is not the determinant of g, but it's the determinant of the inverse of g. So this will give us epsilon times the determinants of the inverse of g, which is of course the inverse of the determinant of g. So this will give us here 1 over g factor times a Levi-Civita symbol, which we now put its indices upstairs. As we said, it doesn't matter upstairs, downstairs, for the symbol it is the same, times the square root of g. Now we see that square root of g defined by g does not give us simply 1 over square root of g, because g can be positive or negative. So if we consider the definition of the signature of the metric, this will give us minus 1 to the s divided by the square root of g. So that n vector is also a Levi-Civita tensor. And as you see, we have defined it in such a way that its indices are raised by the inverse metric. The penalty we have to pay is we have to have this inconvenient minus 1 to the s here. In some literature, you will find this minus 1 to the s missing here, but don't be alarmed, this is just a convention for convenience. But of course, each time we have to know the definition in order to do computations correctly and in a consistent way. So the contraction identities that we computed for the Levi-Civita symbols carry on identically to the Levi-Civita tensor, except for the signature of the metric. And the reason why they carry on the same way is because when we contract the epsilon tensor with all indices up and with an epsilon tensor with all indices down, the square root of g of factor is inverse to each other, and it simplifies. So all you're left with are with contracting Levi-Civita symbols. So the properties are the same if you take into account this minus 1 to the s factor here. So let's write down those expressions. So here we contract p indices of the tensors. So by applying the identities that we computed for the Levi-Civita symbols, this is n minus p factorial times the n minus p delta symbol, and then we have this minus 1 to the s here. Now if we contract all indices but the two last ones, this is an identity that can be useful. And then of course the identity that is obtained by contracting all indices. That will give us n factorial, but there is this minus 1 to the s sign here. The existence of a nowhere vanishing n form on a manifold allows us to define dual forms. So let's start by defining these operations on p vectors, and let T be such a p vector. Being a p vector, it means that it is a 0p tensor with all its indices being antisymmetric. We define the dual of this p vector to be an n minus p form. So this can be confusing, but when we write down the expressions, the upstairs and downstairs placing of the indices reminds us how to do that the correct way. So actually what we do is we contract the n form with the p vector by contracting the first indices of omega with all the indices of t, and then you see that there are here n minus p free indices that will be the indices of the object on the left hand side. Now, because these indices are downstairs, that will be an n minus 0 n minus p tensor. Because they are antisymmetric, that will be an n minus p form. So the dual of a p vector is an n minus p form. So of course this duality is defined with respect to the chosen form omega. Of course any other form will differ compared to omega by just a function on the manifold M. So the definition with respect to different forms differ only by this function f. In order to define duals of p forms, we have to consider an n vector that will be called the inverse of omega. First of all, notice that an n form has only one independent component. All the rest are obtained by permuting the indices and multiplied by the sign of the permutation. And of course this is consistent with the fact that all n forms are proportional to each other. So if we consider this nowhere vanishing component of the form omega, and we just pick the 1, 2, 3 through n component, we define an n vector whose only independent 1 through n component is the inverse of that of omega. And of course, if you contract the indices of those forms, because there are n factorial such terms, you will obtain n factorial, not just 1. So we use this inverse, which is an n vector, as we just said, to define duals of forms. So if Xi is a p form, then we contract all its indices with the first p indices of the inverse form omega. That will leave n minus p free indices upstairs. So that will give us an object which is an n minus p vector. And of course it's an n minus p vector because these indices are completely antisymmetric. Having defined duals of both forms and vectors, it is interesting to see what happens if we apply the duality operation twice on either p forms or p vectors. So let's consider the dual of a p vector first. So here we have taken the dual of the dual t, and since this is a n minus p form, this is obtained by the contraction of n minus p indices of the inverse omega. We have here n minus p factorial because of this, and this leaves p free indices upstairs. So this is a p vector, similar to t. Then we substitute the formula that gives the dual of t, the dual of t is a p vector, so its dual is an n minus p form, and it is obtained by contracting omega with t. The first indices of omega are contracted with all indices of t. So you see all those indices here are contracted, leaving mu1 through mu p to be free. So we move this p factorial factor here. We also leave this alone, but now rewrite this the component of the n form in such a way that all these nu1 through nu n minus p indices have been moved, are moved, in the first positions. So in order to do that, each index has to jump over p indices, each time giving us a -1 to the p factor. And that has to be done for all n minus p indices, giving us an overall -1 to the p times n minus p sign. But now, what we are left with is with this form here, to have these indices contracted, and because this is the inverse of that, then this is the same as contracting Levi-Civita symbols, because omega 1 through n is 1 over omega 1 through n of the original one. So here we obtain an n minus p delta symbol from the contraction of n minus p indices, and that will leave free mu1 through mu p and lambda 1 through lambda p. So we do some simplifications here, and we also substitute the p delta symbol here by its equal, expressed as products, as sums of products of delta functions. So this is a p delta symbol, so there is a p factorial times the antisymmetrized product of deltas, and this is the same as having the products of the delta functions, See here, this p factorial drops out. The sign is put here in front. And here we have the simple product of delta functions because lambda 1 through lambda p are completely antisymmetric. So contracting with the antisymmetrization will give the same result as without the antisymmetrization. So now these are simple delta functions that replace the lambda indices with new indices, and we derive the result that the dual of the dual of t is equal to itself up to a sign, and that sign is given by this minus 1 to the p times n minus p factor. A similar result can be obtained by following the exact same steps for p forms, and the relation is exactly the same. Now, if we have a metric and the corresponding Levi-Civita tensor, we can apply those formulas for duality, except now that we have to be careful that the Levi-Civita tensor with indices upstairs is not the inverse of the n form with the indices downstairs. So we can define duals by considering the tensor Levi-Civita with indices downstairs, and the inverse, which is the Levi-Civita with indices upstairs multiplied by the signature of the metric. This is not what is usually done in the literature of general relativity, and for the duality, the Levi-Civita tensor is used without the sign coming from the signature of the metric. So we have to be careful to carry this sign correctly in the formulas that we will write. So this is not a problem for defining duals of p vectors. We just use the Levi-Civita tensor to obtain an n minus p form, as we did with omega before. But now, the metric, we know that the metric defines a one-to-one mapping between p forms and p vectors by raising and lowering indices. So the p vector here is completely equivalent to the p form there by raising the indices as we had shown before. So we can substitute the p vector here by the equivalent p form there and obtain this equation. And if we define this tensor here, which is obtained from the Levi-Civita tensor by raising the first p indices with the metric, we obtain this equation shown here in this line. But you see that this equation here defines the dual of a p form to be an n minus p form, something that it was not possible when we don't have the structure of a metric. So the Hodge dual of a p form is an n minus p form defined by this equation, where this is the Levi-Civita tensor with p of its indices raised by the metric. With this definition, we have to be careful. when we apply the duality twice, we obtain back the form we started from up to a sign, but now the sign here, except from the factor p times n to the minus p times n minus p, has also a sign coming from the signature of the metric. So this sign here comes, if you try to do the computation, from the fact that now epsilon, when the epsilon tensors are contracted, we don't obtain n factorial as we did with the n form omega, but minus 1 to the s times n factorial. It is nice also to observe that the sign here, it looks complicated, but it can be stated in plain English, especially in odd dimensions, like in 3 dimensions. So in 3 dimensions, this product here is even for every value of p. So in that case, taking the dual twice brings us back to the original. Assuming, that we have a metric with a positive signature, as is the case of the ordinary Euclidean space. In 4 dimensions, or generally in even dimensions, this sign here has the parity of p. So it is plus for even p and odd for odd p. Now, depending on the signature of the metric, that of course might change this result. And this is indeed what happens when we have a metric with minus 1 signature, like we have in special relativity or in general relativity. So here, if s is equal to 1, then the sign here has the opposite parity of the integer p.